huge amounts of vibration that are trying to shake your circuit boards apart. You've got the threat of lightning strikes, electromagnetic interference, interfering with the circuitry and the software in your system. And all that results in everything costing a huge amount of money and everything running really slowly. You might think your, I don't know, 3-year-old, 4-year-old PC is running a bit slow now when it's running Windows. The systems on these jet engines are kind of running at 40 megahertz or something like that. Really sort of 10-year, 15-year-old technology, because it's known to be safe and it's known to be reliable and it's known to be robust. So we have to fit within those constraints to make our algorithms work in spite of the limited amounts of memory and processing power and sensing that we're allowed to put on the engine. Okay. So this is just a diagrammatic picture of what we try and do at the UTC to assist Rolls-Royce's problems. The one I'm talking about today is all about the health monitoring for what are called the accessories that sit around an engine. To make an engine work, you need obviously your compressor to suck air in, squash it down, a combustor where you throw fuel in, burn it, and a turbine section that spins around as the gas expands. That's the basic principle of a gas turbine engine. But to make that work, there's a huge amount of engineering in all the systems that surround that engine. You have to be able to start the engine, you have to be able to lubricate the bearings, you have to be able to pump fuel, accurately measure fuel, you have to be able to move control surfaces within the gas turbine engine in order to make it perform optimally. You also need to move control surfaces to stop it having anomalous behaviour. So there are events such as if you get it wrong, you can get a pressure difference the wrong way inside an engine. So the pressure can be so high in the centre of the engine and so low at the front that the gas comes out the wrong way and it's on fire. So you get a big fire plume coming out the front of your engine, which is obviously something you want to avoid. So there are all these systems that have got safety and fuel consumption reasons for being there and to make the engine function correctly. So we at the UTC look at actuation, hydraulic actuation, electrical actuation, looking at pumps, what else? Servo valves, so positioning valves within the system, and I suppose we look at the faults that could happen with those, and what are the signs of degradation that might occur. So we've got that domain that we look at, all these parts. We then want to say, okay, what's really worth our while looking at? What are the things that are causing problems in service? So we try and model the benefits of what would happen if we put some EHM on. How much value add would it give? Next level up, we then design and analyse software algorithms that meet those requirements that we've derived. And today, the top two are two examples of those design and analysis systems. We look at some prognostic algorithms. Prognostics, once you've done your diagnosis, how can you predict ahead into the future to see what's going to occur in a week's time, 3 months' time? And also, if we've got time, look at some systems we've looked at for isolating faults. So we know something's gone wrong. How do we know what the maintenance action ought to be? How do we act correctly on that system? Okay. I think it's reasonably fair to say that in the past, health monitoring's been done in a fairly ad hoc way. People have sort of thought, oh, what might go wrong to this product? What sensors and means have we got that might help us detect that? And the problem is that although you develop all these techniques that work, you don't assess whether or not they're really doing the right thing. So we've introduced into Rolls a process of assessing the benefits of health monitoring. And we do that by taking a system and breaking it down in what's called a functional modelling sense. So we take a component, let's say we take a, let's say, I'll keep with the gas turbines, we take a fuel pump on a gas turbine. What's the function of a fuel pump? The most obvious function is to deliver fuel into the combustor. Another function of it is to provide pressure to the control surfaces so we can move things around. Another function of it is to provide fuel flow that we use to cool the various components. These are the functions of the system. We then say, okay, how can those functions fail? What are the ways in which you can stop delivering the right amount of fuel, etc. We then say, okay, what might the functional effect be to that failure? Is it going to cause, in our terminology we say, is it going to cause the engine to stop working? Is it going to reduce the efficiency? Is it going to mean that we're not allowed to fly our aircraft? Is it going to mean that passengers are kept on the ground waiting for the plane to be ready? And each one of those different scenarios, we can say that costs the airline X amount. So these functions link down to how they might fail and the cost of that failure, the monetary cost. And then we say for each functional failure, the way it can fail, what are the causes of that? What things can go wrong that would cause that function to go wrong? And then the final stage is looking at, okay, what are the symptoms of that failure? What are the things, the very small changes that we expect in our product to lead ultimately to the aircraft not being able to take off or it being delayed. By taking that approach, we've then got a big list of small symptoms that we might expect to see when something goes wrong. And each one of those symptoms, we can trace back up our, this is a database here, we can trace back up our database and see how much, if we could detect that symptom, how much money would it save? So let's take, for example, if I could detect a worn gear inside a pump, that might be the incipient effect of a future failure of the pump. What does that pump do? Well, there's lots of different pumps. Let's say it's a I'm trying to think of a non-critical one. Let's say it's a pneumatic pump that's driving the icing system on an aircraft. So it's driving something, but it's not absolutely safety critical. You could still take off without that particular system, let's say. That's got less value being able to detect that particular fault than something which would cause the engine to actually not work at all. So the assessment of the value of these incipient faults, these symptoms that occur, allow us to direct our research, and we choose the most valuable items that we look at and develop algorithms for. Okay. So composed of functions, functional failures. Those functional failures have an operational effect, and the functional failures are caused by something going wrong, a failure cause. Each one of those failure causes has got a predictable rate and a repair interval, and then those failure causes have got incipient signs, symptoms of the fault happening. Okay, so we apply some analysis to that, and we can drag out an optimal surface for what type of EHM system we put on the system. We can evaluate each possible combination of components on that system. Okay, so I won't go through that. We also look at, once we've decided what we want to do, we then need to decide where are we going to put it. So we've got the what, looking at the where now of where we place these things, and this is all about evaluating whether we should put it on the wing, on the engine itself, on the aircraft, on the ground station. And we've got a current program looking at how to optimise that allocation of functionality. Okay, so optimise that based on a model of the costs and various constraints. So, a couple of case studies of once we've decided what we want to do and we've made sure that we've got a suitable place to put it, if we do decide to do it, how do we go about developing algorithms with real data that we can take to a high confidence of maturity? Okay. As I said before, the biggest problem is that things are too reliable and we don't have failure data. What we often have to do is look around for people who are doing tests that might create the kind of faults that we expect to see. And this is Sheffield on the map there. And out in Sheffield, one of the mechanical engineering professors has got a small facility where he's doing some work on what they call the stability of fuel. When you put fuel and you heat it up, the chemistry can change and it can start kind of degrading. That's a big problem on an engine, because if your fuel starts degrading, what happens is all these gunky sort of these sort of gums can come out of the fuel, and it becomes really sticky and really viscous. And that viscosity increase can start coating valves and components within the engine. We want to be able to predict that that's happening. We want to be able to tell that that's happening and predict how long we've got before that starts causing issues. So we're doing some work with a facility out here where they've got a rig which takes a big tank of 10,000 litres of kerosene, and they run a 300-hour test of this aviation fuel, pump it through the system, heat it up, so there's two pumping stages. They take it up through the system, heat it up to temperatures which are similar to what you get in an engine. They pass it through various filters along the way, and in the end they inject it through a pipe that represents the combustor of a gas turbine engine. They don't actually burn the fuel, they just squirt it out, but it's all heated up. Over the course of several hundred hours, you start seeing the effects of these lacquers building up within the components. And every 10 hours, what we've been specifically looking at is a valve in this system, which we open and close every 10 hours and monitor the behaviour of that valve and see whether the response is changing of that system. And that's the valve in, you can't really see what's going on, but in there is the valve which is opened and closed over this long endurance test. And from that we've been collecting data at nice high sample rates. Might work. No one's tried to do that before. We'll come back to that, shall we? Oh. Okay. So let me start. Right, this is data we've collected from this valve, and the way this valve works is, let me get this right, is that we can measure the flow rate, which is on the y-axis, and the pressure across the spools. So if you imagine there's some flow that wants to come from you to me, and there's a valve here that either opens or closes depending upon the position of this valve. There is some force acting on either end of this spool that can move it left or right. When the valve's nice and smooth and there's no problem with it, the valve will move very smoothly across like that as you change pressure. When there's this lacquer building up on the system, we get a very sudden movement of the valve as the